Testing. Okay, today we're going to finish up our limits. This is lecture number 9. Yesterday, just to recap, we talked a little bit about the notation, the growth in the early use of symbols in the mid-1700s, sort of geometric and graphical understanding of functions that existed in the early days of calculus before the analytic analysis formulations developed. We have an example of the applet function to do graphs, the relationship of an inverse function, the implicit function theorem, continuity, differentiability, etc. And we also talked about several of the early questions that arose whenever functions were first identified as sort of objects of their own interest. And that is every function continuous except at a finite or countable number of points? And the answer is no. Is every function continuous except for a set of measure 0? And the set of measure 0, in case you haven't seen that term before, is the following. If you take a set of points on the real line, if they're discrete points, clearly you can put them in intervals that contain only those points and let those shrink to 0. So the measure of the size or the volume or the area or the length of those intervals can become arbitrarily small. Now, if you have a set of numbers like the irrationals, that's harder to do. But the idea is you have a set of measure 0. If you can cover the set inside a series of balls or disks or lines whose total length approaches 0. So that's the concept of it's a measure 0 if you can cover the set by lengths or intervals or balls or disks or whatever have you, so that the summation of the lengths is arbitrarily small. So given any small tolerance, you can cover a set by the length of intervals that are smaller than their epsilon. If you can do that for any epsilon, then the set of points has measure 0. Now certainly discrete points have to be a set of measure 0. But you can have an infinite number of points with a set of measure 0 also. Similarly, most people thought in the early days that functions were nice in the sense of being differentiable, except possibly with a set of measure 0, points of discontinuity, for example, or kinks or corners or cusps. That is now known not to be true. You can have a function which is everywhere continuous, and nowhere does it have a derivative. That's the Weierstrass function. Question is the limit of a sequence of continuous functions continuous, and the answer depends on what you mean by limit, but in many cases the answer is no. So these were early questions that caused them to explore the idea of functions and the nature of limit much more carefully. Now today we're going to talk a little bit more about what we mean by limits of functions, and in particular sequence of functions, because often we generate a sequence of functions, f1, f2, f3, etc., and we want to know what is the property of each fn, and is that property preserved in the limit. And I'll talk a little bit specifically about solving a differential equation later on. So there's some obvious choices of what we mean by this idea of the size or the length of fn minus f. Now, whenever you see a double vertical bar, that's the norm. A single vertical bar just has to do with a real number, a complex number, but double bars mean norm. Now, norm is a distance just like absolute value. And in fact, the norm has to satisfy three properties. Namely, that the only objects of length 0, the only object of length 0 is the 0 vector. That has to be one of the key properties. Also, it scales linearly in the sense that if you take a object, multiply it by a constant k, then take the size of that, it scales by the absolute value of k. So in particular, if you go from x to minus x, it has the same length. And finally, this is known as the triangle inequality. This says that x plus y is less than x plus y. Now, it's called the triangle inequality clearly because if you have a triangle, say here's one, and here's one, then actually probably that's not x plus y. So if this is x down here, and this is y, then x plus y is actually the other hypotenuse here. So this is x plus y. And this line is just the translate of y. So this says that this is the distance x, this is the distance y, and this is the distance x plus y. So clearly, x plus y, the diagonal, is less than the length of the bases of this right triangle. So that's called the triangle inequality. If this property, this double bar norm operation, if it satisfies these properties, then we can use it to examine convergence, because this says that the distance between fn and f goes to 0. Now in functions, there are an infinite number of choices for your norm. Three of the more common ones are the first one, which is called the max norm, because for a closed interval d, you just take fnx minus fx pointwise, and you see what the maximum value or the sup value is, or the maximum value over the interval, absolute value, and then that's the greatest distance that two functions are apart pointwise. If that goes to 0, then you have essentially uniform convergence. Yeah. Yeah, so it was better to use the sup norm, but that was a technical thing for the distant students that I didn't really want to get into.
Okay.
Yeah, it may not actually achieve the maximum because it could be an open interval and things like that. So,
right.
So we should really say sup norm. Another different distance concept is what we call the 2 norm, which involves the integral. If you take fnx as a function, subtract fnx, you get a function. If you square it, and if the result has an integral, and then take the square root of that, that's called the 2 norm, or the L2 norm of fn minus f. This is a very important norm because it comes from the inner product and defines what is called a Hilbert space. This norm is essentially replaces p by, or 2 by p. So you take fn minus fx, raise it to a power p, integrate it, and then take 1 over p as the result. And this is actually valid for any p, well, strictly speaking, greater than 0, but it's only really useful for p bigger than or equal to 1. And it does have the property that if p goes to infinity, you essentially get this with the sup replacing the max. So the idea, though, is that anytime you have different norms, they're not all equivalent in the sense that you can have a sequence which converges to 0 in one norm and not in another. So, for example, you might have a sequence of functions that converge in the sense of their area to 0, but not in terms of their height. So, for example, if I had a function that oscillated around like this, And then you gradually move the oscillation in here, so I had a sequence of functions that oscillated greater and greater frequency, but always had a range of a certain value. It's possible for the area of a function to go to 0, but the maximum of the function does not go to 0. Okay? An easy way to think of it is a series of functions that looks like this. Just define fn of x to be 1 at the origin, 1 over n here, and this goes to 0 in L2, because clearly, if I take fn squared dx, square root of that, what is it? It's just a height 1, and so this gives you 1 over n, which goes to 0, but the maximum value of fn is 1. So clearly this sequence cannot go to 0 in the first sense, but it can go to 0 in the second sense, because fn squared is the same as fn minus 0. So fn goes to 0 in this sense. In fact, fn goes to 0 in any LP, but not in the limit. So this could even be p there. Okay, so the important thing is when you have different ideas of norm, different ideas of distance, you have different notions of convergence, and in some cases functions may converge to one another, other times not. Now, one of the important things, one of the very important objects in mathematics is something called a function space. Which is just a set of all functions, and such that their size is finite. Okay, so this is just a normed space, and you have the ideas of distance. So the combination of a functions and a norm is extremely important. So if this norm is LP, then you have LP spaces, and you can have Hilbert spaces, Banach spaces, all kinds of function spaces. And studying convergence is one of the things that people do all the time, and limits, in other words. Okay. Now we can extend the idea of a function. By function, I mean a pointwise function. So like f of x equals x squared. Now you can do function composition, but there's another way of operating on a function to get a function, say for example the derivative. If I take a differentiable function, say sine of x, and I hit it with d over dx, that gives me cosine of x, and that is itself a function. So d applied to sine is a function. So if d is the derivative, then d of sine of x is the derivative of this is cosine of x. So I put a function in and I get a function out. This is called an operator. It's not really a function, because it's a function of a function. And I often use square brackets when we talk about operators. So I use square brackets instead of curly brackets. Obviously, integration is another function. The integral of a function is itself, or the antiderivative, is a function. And these are, in fact, examples of what are called linear operators, because when is a function linear? L is linear if it has exactly the properties you would think, namely, if I take L of the sum, that's the sum of the L's. And if I take L of a constant, scalar constant, I get K, L, or G. Many important questions remain even with linear operators. Nonlinear operators are functions which are not linear. So a nonlinear, not everything is linear. A nonlinear operator might be d of f equals f of x, f prime of x. That's a nonlinear operator of f. Solving equations with nonlinear operators is, of course, much more difficult than linear operators, and it's hard enough solving linear equations. Now, of course, you might ask, why is it hard to solve a linear equation, right? Don't you learn how to do that in elementary school? Well, as a parenthetical remark, what is the problem with solving linear is the fact that the space or the dimensions of the spaces become infinite. So what could possibly be the problem? I mean, if you have y equals ax plus b, you can solve that for x as y minus b over a. What's the problem with solving a linear equation? Well, an example of a linear equation might be the derivative, second derivative, plus act on y plus x times y of x equals cosine of x on 0, 1 with boundaries. Say y of 0 equals 0 and y of 1 equals 1. That's non-trivial. That's a linear equation. This preserves sum and matrix scalar multiplication, and so does this. It's linear in y, but this is not a trivial problem to solve. And the problem is that if I were to look at the set of all functions with finite norm, this can have an infinite basis. So, for example, sine nx is in this space, usually. Right, certainly for the suit norm and L2 norms. But all of these are linearly independent. And if I have a bunch of linearly independent functions, if they completely describe the space, then the number of them is the dimension. But since there are an infinite number of functions with finite size, and they're all independent, this means that the dimension of that space must be infinite dimensional. So this is infinite dimensional. That is the problem. Because when you have an infinite dimensional space, then it becomes more difficult to pin down null sets, things that get mapped to 0, and uniqueness and all this kind of stuff. At the very bottom, there are some open problems, which I'll describe to you in just a second. Extremely important application, particularly for people of applied orientation, is that very often when you want to solve an infinite dimensional problem, you approximate a problem by a finite dimensional problem. So, for example, I might do this, and this is a classic example. I would take a region here, say 0 to 1, and I would look at the equation dy dx equals y of x, and say y of 0 equals 1, and that, of course, actually has the unique solution e to the x. So it looks a nice little function like this. What you can do is, of course, divide up these intervals in the finite difference method to intervals of length h, say, which is 1 over n. And then you just approximate the derivative on the left, this on the right, and then that gives you, of course, if you solve for yn plus 1, this would be yn plus h yn, or 1 plus h yn. Now what you get out of here is a piecewise continuous function. it takes on values. Each value is 1 plus h. So at the very limit, y sub n plus 1 is, of course, 1 plus h to the nth power. Now, the question is does 1 plus h to the nth power actually converge to 1, or e rather, either 1, as n goes to infinity? Well, you'd say, well, how can that be? Well, remember, h is, as n goes to infinity, h is 1 over n. And in fact, you can show that the limit as n goes to infinity of 1 plus 1 over n raised to the n power is, in fact, e to the 1. So actually, this is a finite, each one of these is a finite problem, and this piecewise linear function with approximates the exponential.
It comes in a Taylor series and
yeah, that's right, yeah. Yeah, this is Euler's method, and it does come from the first order Taylor series.
I'm talking about the approximation, or what the limit is.
Oh, this one?
Yeah.
Yeah, it's sort of a combination of L'Hopital's rule and limits of the form. I mean, if you put in this, well, it's actually, maybe I should say there's a problem, but this, if you just substitute infinity, this is of the form 1 to the infinity, which is one of those, like L'Hopital's 0 over 0. So you can look at this. If you take the logarithms of this is n log 1 plus 1 over n, and you can look at expressions that look like 1 over 1 plus n divided by 1 over n. Now, as n goes to infinity, this is log of 1 plus something over this. So log of 1 is 0, 1 over this goes to 0. So this looks like 0 over 0. So then if you differentiate it, then use L'Hopital.
Okay.
And then if you know what the log of the limit is, if this goes to 1, if the log of the limit goes to 1, then the limit itself goes to e to the 1. So it's just a combination of actually it doesn't use Taylor series, but it uses L'Hopital's rule for continuous functions. Anyway, what we've done is we've approximated a finite dimensional problem or infinite dimensional by finite. Each of these is trivial, and what we've shown is in the limit, the finite version of the problem solution will converge to the smooth continuous version. Now, that's kind of a simple example. A more interesting example is if you have a two-dimensional object like this, maybe you have holes in it like this, and you break it up into triangles. So you might have what's called a mesh, and you just break this up into lots of little bitty triangles. So you define what's called a mesh. And again, this makes it into a finite dimensional problem. And the fundamental question is, if you have a linear problem, say with derivatives in it, and you're solving this problem, can you approximate it by a finite dimensional problem with u sub n and solving this equals fn, but now, since these are finite dimensional, this is finite dimensional, this is basically a matrix. And we can solve this for any n. Okay, the question is if the right-hand side converges to f, does the limit approach u? That's the $64 question. Because it's easy to come up with a sequence of right-hand sides to get closer and closer in a function sense to f, and it's easy to solve any of these for a finite dimensional problem, but the question is as you let n go to infinity, and the right-hand side approaches f, does the inside u sub n approach u? That's the question. That all has to do with convergence of subsequences and sequences. So if you have a linear problem like so, where u and f are functions and L is linear, and you can find the solution of the finite version of the problem, and you can furthermore approximate f as by fn as n goes to infinity, do you have a solution of the original problem? Well, I'll give you an example of that where we don't use finite dimensions, but we use a slightly different idea, namely Fourier series. So suppose I were to have a problem where I have an interval 0, 1, and suppose I have minus the second derivative of u plus the first derivative of u equals some function of x. And furthermore, I say that u of 0 is 0, and u of 1 is 0. So think of this as sort of being like a string problem where you're supposed to get the deflection of a string. It's anchored at these 2 points because u equals 0 and u equals, actually let's make this pi for convenience. Now, suppose I had a very simple function, u sub n equals sine n of x. Now, it doesn't satisfy this equation necessarily, it just satisfies the boundary condition. It's just an oscillatory function on this interval. But if I put it into this equation here, what is minus the second derivative of u plus u? Well, what's the second derivative of sine n of x? It's minus n squared sine sine, so this is a plus n squared plus un is sine nx. Now, I can't really solve that for arbitrary f, but I could solve it if f is that form. If f looked like a constant times what? Sine nx, could I solve this problem? Well, actually, I should put an unknown in here because we call that an times sine of x. So then this is an times that, an times that. So we would have n squared plus 1 times an sine nx would be c sub n sine nx. And we could, of course, solve for this because we know n, we know sine, we know the right-hand side, and we're trying to solve a. What a is just what? If I cancel the signs, an is just 1 over 1 plus n squared times cn. Okay, so you say, well, what does that buy you? That really wasn't the problem, right? F is not purely a function of sine n of x. But suppose I could approximate it by a linear combination of such things. Suppose, in fact, I have a linear combination of signs going from, I skip 0 because n equals 0 just gives you 0, going from 1 to infinity, and I want to solve this problem. I claim it's very easy because I just insert a series that looks the same way of a sub n sine nx, that's my u, and I put it into this equation, and that would give me n squared plus 1 times an would be equal to Cn. So what would be my solution? It's just my right-hand side, Cn nx, but I divide each term by 1 over n squared. Now, what do you notice about these terms here? What does the 1 over 1 plus n squared do for you? It goes to 0, in fact, more rapidly than Cn, so it increases the convergence of the series. So series which are more rapidly convergent are in general more smooth. And so what's happening in here, remember, sort of roughly speaking, when you differentiate a series, you pull out an n, and when you integrate a series, you pull out something like a 1 over n. So this is like 2 integrals of the series, and when you integrate something twice, you give it 2 extra degrees of smoothness. So if f, for example, is just continuous, how smooth should u be? Well, 2 derivatives, right? Because the second derivative of u has to be comparable to f. So this is actually smoother, more convergent than the original function f, and in fact, if f is continuous, you should have 2 derivatives. Okay, so this is an example, and of course, if fn goes to f, what does that mean? That means you're picking up more and more of these Fourier series coefficients. As this goes to f, of course, un will go to u. It will go to a solution which in fact is the solution of the problem in the limit. So this is an example. It's not finite differences or finite elements or any other, but it's an example of approximation by a sequence of functions. And if you think about it, it's impossible to solve an infinite dimensional problem on a computer. You have to approximate it by a finite dimensional problem. If you have a finite dimensional problem, the question of whether you actually can solve it in the limit is exactly a sequence convergence problem. Does the sequence of functions u sub n converge to u if your right-hand side fn converges to the real fn? Another problem, and this was one of the early problems, it's related actually to Fourier series, and I would call this a moderately hard problem, and that is, does the linear operator have an eigenvalue? Now an eigenvalue, eigen meaning special, the eigenvalue is just a value, say lambda. I couldn't write lambda in the HTML, so I'll write it here. If you take L, and suppose you have a function like this, and you map it on with L onto another function, if it's just a scalar multiple of the original function, then this is called an eigenvalue, and of course this is called an eigenvector, or in this case, eigenfunction. If it were a matrix, it would be an eigenvector.
Yeah.
Okay, so the question is does a linear operator always have an eigenvalue? Does L always have an eigenvalue? Other than the origin. I mean, lambda equals 0 is sort of well, it's a trivial solution. If L has anything in the null space, then that's sort of like an eigenvector, so eigenvalue. So the question is you can ask about 0, but you can also, L could be complex, lambda could be complex, real or complex. So the existence of eigenvalues, whether they're bounded or not, so there are many, many deep questions. So here are some questions about eigenvalues, which are not easy to answer. So question 1, are they finite? I mean, can you list them, lambda 1, lambda 2, etc., lambda n? The second is, are they bounded? That's usually the easiest. Are all the eigenvalues bounded? They could be. Do they converge? In other words, do the eigenvalues converge to, say, 0? Do they pile up at the origin? Do they even exist? Because there is something called the spectrum, and the spectrum includes both discrete eigenvalues like these and also continuous spectrum. Like I could have an interval of lambdas versus discrete lambdas. When you have an infinite dimensional operator, you could have both kinds of spectrum. For example, the derivative really has continuous spectrum if you don't have boundary values, because if you look at f prime equals lambda x, the derivative, say, of f equals lambda f, this has a solution f equals either lambda x. That really exists for all lambda. So it doesn't really have discrete spectrum without giving boundary conditions, or even if I gave boundary conditions, f of 0 equals 1, this is a solution for all lambda. So it has continuous spectrum. Now, the spectrum has a physical property associated with energy states, like the eigenvalues of Schrödinger equation give you the bound wave states of the atom and all that stuff. So, physically, the eigenvalues are very important. But here's an unsolved problem related to functions, and it's sort of a generalization of the eigenvalue problem, and that is, if you look at a set A, this is a set of x points, and L of A is just the image of A. What does that mean? That means it's a set of all y, so that y equals L of x, where x is an element of A. So the question is L of A contained as a subspace of A? If this is true, then you can keep taking points in A, look at its image, you get L of A, that's in A, hit it with L again, and you keep on taking it. So a fixed point, for example, might be, or the point, if A is a subspace, a closed subspace, then the existence of A is called the invariant subspace. So if A is a subspace, linear subspace, that means it contains the origins closed under addition. If L of A is contained in A, then it's invariant. Invariant meaning it's like the eigenvalue, because if you look at the eigenvalue, what does that mean? If L of U is lambda U, if you look at the span of all U's, all linear combinations of U, that's a linear space, it's just an array, then this says that it's contained in the same space, because you're just multiplying the space. If you take any vector and multiply it by lambda, in the subspace, it's still subspace. So this is the invariant subspace if it contains this problem. The question is, do all linear operators have an invariant subspace? I mean, you can give lots of examples, like the identity operator obviously has one. Things with eigenvalues have one. So anything with an eigenvalue, you can just take all linear combinations of eigenfunctions, and that would be an invariant set of space. But that's one of the deepest problems in this area of mathematics, which is called operator theory, is does this linear operator have an invariant subspace? So we ignore 0, and obviously it's true if you take the whole space itself. If A is the whole space, L of A is contained in the whole space, but we don't include the all or nothing, the 0 and the A itself. So the invariant subspace problem is actually, there's a faculty member here called Percy who was, actually I think he was offering a course on this at one time. So we have some experts in the department. This is probably one of the biggest, I should say one of the biggest open problems. You may not get $1 million for this, but you'd be world famous if you solved it. Okay, so this pretty much ends up what I want to say about functions. Functions are relatively recent in terms of their notation, just dating back to Euler in the 1730s. Leibniz exploited the notation to develop the calculus. Newton had a more graphical understanding of functions. And it's sort of a flavor. You can understand functions through their graphs and functions through the sort of analytical expression. Now, under unusual functions, we've already talked about some functions, the Cantor function, the Weierstrass function. What I wanted to mention here, just into this last dimension matters, is just to give you a little sideline into elementary differential equations in 2 dimensions. For example, if you have a differential equation, say of first order, first order ordinary differential equation. What does that look like? Well, it's going to look like the following. And we'll write it in somewhat simpler. The derivative of dy dx equals f of xy. Now, if I don't have an explicit dependence on x, so call that capital F, this is then called autonomous. Autonomous system. Now, if you look at this very carefully in what's called the phase plane, suppose I have a point here, x and y, and I have a solution, y of x equals y naught, so it comes from this point. Is it possible for me to have 2 solutions that branch out of this point? Well, if you look at this, if this is dy dx, how can dy dx take on 2 values if f of y is a single-valued function and you're applying it at y0? So if f is a single-valued function, you cannot have 2 solutions that emanate from the same point. Okay? So this is just another way of saying that you have a unique solution. Well, you can't have 2. You may not have a solution, but certainly if f is sufficiently nice, you can only have a single solution. So this can't happen. So let's erase it. So you can only have one out of here. So, but that really limits what can happen as a solution. So if we look at what's called the phase plane, and this is a purely graphical tool to understand the system of differential equations, we just look at x values and y values, and we start off at a point where the initial condition is, and then you just let the whole thing wander around aimlessly in the phase plane. Now, what can't happen is you really can't cross in finite time. Okay? And that limits you to what you can do, because if your function is bounded, there's really only a couple things you can do. You could have all the orbits, this is called an orbit or a trajectory, They could all come piling into a point here, or they could all leave a point. Now remember what I said about finite time. If you look at a case like dy dx equals y over x, you could write this as dy over y equals dx over x. Integrate both sides. Log y equals log x plus constant, or y equals some kx. So all of these are lines, and the fact is you never really reach it in finite time. So you could have behavior like this, but there's only a few other cases. You might have a spiral, or you might have a periodic orbit, like sines and cosines. So this periodic orbit, this is called a node, this is called a spiral, and can go to a direction. These are really all that you can have, because what you're prohibited in doing, you can't just have like a random mess like this. That can't happen in 2 dimensions. So in fact, I'll make this, I'll put my big symbol through that. You can't have that. The reason being is because if the trajectories cross, you don't have your unique solution there if it's at finite time. Now, of course, if this is not true for general, if there's an x here, where's my? Here it is. If there's an x there, you can have this, because when these cross, it's at different values of time. So that's why it's autonomous. But look what happens in 3 dimensions. In 3 dimensions, all bets are off. And that's why you can have chaos in 3 dimensions. Because in 3 dimensions, I'm in a cube instead of a square. And if I start off my trajectory here, I can go around here, and can I cross over it? Well, the answer is yes in 3 dimensions, because you're just crossing above it. It's like having, can you have a piece of arbitrarily tangled spaghetti? And the answer is yes. I could have just a mush of spaghetti that looks like this, and these never actually cross at the same point. So the trajectory could be arbitrarily complicated in 3D. You can have very complicated phase planes. In fact, the Lorentz attractor has such a phase plane that you can even say that it has chaos. Can't write. You can have chaos, which is the property that you maybe oscillate around a little while, and then all of a sudden you randomly jump to another point, then go back and spin around and jump. But this can't really happen in 2 dimensions because there's only a few types of behavior that are permitted. So this is basically called a node. This is a node. This is a spiral. And this is a closed periodic orbit. And it's a relatively deep theorem in differential equations of a single variable first-order equations, so your phase plane is 2-dimensional. That's all you can have. You can have node spirals and periodic orbits, but that's it. Okay, so dimension does matter for functions. And the graph of the function, of course, contains all the information of the function, but in a way that's not really amenable to analysis. You may have lots of intuition on a graph of a function, but you can't add graphs, you can't subtract graphs or divide them. I mean, you have to have representations of functions as analytical expressions to do that. Okay, so the next thing that we're going to cover will be the following. Let me just get Geller and Boaz's book. So in fact, we will cover the Chapter 10, Geometry, Plane Geometry. We're going to have a nice little reprise of geometry. We started off with geometrical problems, squaring the circle and constructing real numbers, and this is going to be some more or less purely geometric problems. We'll get a chance to reinforce your geometrical intuition from high school if you haven't done sort of proofs in geometry in a while. We'll get a chance to do that. I will be posting later on tonight some questions, problems having to do with limits. That will be number 4, and then probably homework set number 5 will have more or less purely geometric type problems.